Hi, my name is Cole Eckelman,
And I'm Johanna Grimsley.
and this is Manning's equation.
So we're going to explain this to you.
The equation is Q equals VA equals 1.49 over N times A times R to the 2/3 times the square root of S. And Q, which we're trying to solve for, is the flow rate, which is in cubic feet per second, velocity, which is in feet per second, area, which is in feet squared.
Then we have our variables that can change. So there's the hydraulic radius, which is measured in feet. And to find hydraulic radius, you take the area divided by the parameter. Then we have slope, which can change the velocity depending on the height of the slope. And we have Manning's roughness coefficient.
And Manning's roughness coefficient changes as whatever's in the water changes, whether it's grass or rocks, or if it's a plastic flume, the roughness coefficient will go up or down. So in order to find the average depth of the water, we take the highest and the lowest measurements and then find the average. So in this case, the average is about 5.9 inches. Okay, so here we have Manning's equation again. Q equals VA equals 1.49 over N, AR to the 2/3 power, square root S. In a plastic flume with nothing in it, the N is given to us at 0.01. The width of the flume was 1.5 feet, and the depth of the water running down at a slope of 1% was 0.225 feet. Now, to get the area for our equation, we did 0.225 times 1.5, which gave us 0.338, and then feet squared. And then to get the wet parameter, we did 0.225 plus 0.225 plus 1.5, and that gave us 1.95. And finally, for our R value, the hydraulic radius, we did 0.338 over 1.95, which gave us 0.173. Okay, so now that we have the equation and the necessary numbers to plug into it, we're going to do the math. So, Q equals VA equals 1.49 over our N, which is 0.01, times A, 0.338, times our R value, which is 0.173 to the 2/3, times the square root of our slope, which is 1%, so 0.01. And after you calculate that, you'll get 1.56 cubic feet per second. So if you think about that physically, that's about, well, it's slow. It's about like that. And yeah.
Okay, so now that we solved for Q in just a regular plastic flume, we're going to find what happens when we have a flume that has rocks in the bottom of it. To do that, you need to start we have our 1.49, which was given. Then we solved for r, which became 0.268, and we solved for that by finding the area again, which was 0.625, divided by the parameter, which was 2.334. Then our slope is going to be the same. It's going to be 1%, so 0.01 to the 0.5. And we use our v that we found over there with v equals q over a. And that is all going to come out to equal 0.0197.
So this is Manning's coefficient. So what we found is so Q, and first of all we should get R based on area and perimeter. So the area is 0.625 and perimeter is 2.334. So A over P will be 0.268. And plugging in this value in this Manning's equation, and then we can get 1.96 to get that.
In conclusion, we have learned that changing what the water runs over changes Manning's coefficient, which in turn changes the flow rate.
Knowing how to apply flow rate to physical hydrology is important in cases like runoff from a mountain,
Rivers.
A drainage ditch.
and such things.
So thank you for watching our video.